sauce. Josh here. It's been quite a while, hasn't it? Well, you know what? That's besides the point. It's the holiday season, and you know what? I love the holidays. I even bought a string of festive lights. Except there's a problem. I bought yellow lights. I would prefer them to be more of a green because it's like more of a holiday color, but you know, I don't want to admit my own monetary failure and go exchange them. But what if there was a way that I could change the color of my lights without having to buy a new string? With science. Now before we talk about how I can change the color of the lights, let's talk about the light bulbs that I bought. I bought LEDs. LEDs are a widespread, efficient source of light, and it's an acronym that stands for Light Emitting Diode. Now let's quickly define what each of these letters mean. If we're gonna talk about light bulbs, let's talk about light real quick. Now light is one of the most confusing things to talk about because it exhibits what's called particle-wave duality, which means it acts both like a particle and a wave at the same time. We're just gonna simplify it and call it a photon. It's electromagnetic radiation that emits from larger bodies. Now, let's talk about how LEDs emit light. Now, when we're gonna talk about light, we have to talk about wavelength specifically. Wavelength is measured in nanometers. And if we look at these are emission spectra in the visible range of light. Now, every emitting body has a certain amount of wavelengths that it emits. If we look at something like the sun, it emits infinite amounts of wavelengths in between the visible spectrum, which is about 200 to 700 nanometers. Something like a helium lamp emits only a few specific wavelengths based on discrete quantum atomic emission energy levels. But looking at an LED, it only emits one specific wavelength of light. Now, not only does only emitting one wavelength make an LED super efficient, but it also makes it a quantum anomaly. To understand that, we have to turn to the final letter in the acronym, D, which stands for diode. So to drastically oversimplify, a diode is a piece of a circuit made of what's called a semiconductor. But before we talk about semiconduction, let's understand quickly what conduction actually is. An electrical current is born when electrons hop from nuclei to nuclei of a set of atoms. Now, all materials on the periodic table can be sort of categorized into three distinct groups: conductors, semiconductors, and insulators. Now, the paths of conduction occur because of the orbitals of the electrons overlapping in what's called a wave function. Now, because of a certain amount of trends like electronegativity and effective nuclear charge, these bands, to say a valence band and a conduction band, where the electrons are and aren't, split apart. In metals, like conductors, the two bands are touching. In semi-metals, they are nearly touching, but in insulators, they're so far apart that electrons could never jump between these two bands. Now, semiconductors are great because you can dope a semiconductor. Doping is changing the atomic structure of a semiconductor to allow it to exhibit a specific, what's called band gap. And this band gap is the key to understanding how we can change the color of an LED, or more so, how an LED ever can emit one wavelength of light. Hey, over here, dude, come on. I've drawn a simple diagram of an LED. We can see right here the semiconductor that allows it to emit light. Now, the band gap of this semiconductor has to equal the amount of energy of the light you want it to emit. So let's say I have a band gap with like an energy of 3.03 times 10 to the negative 19th joules. That means it'll emit a certain wavelength of light with the same energy. So all I have to do to change the color, I guess, is dope my semiconductor on an atomic level and change its chemical properties. Problem though. If it wasn't entirely obvious, I can't dope my semiconductor with new metals on an atomic level. Because LEDs are only about the size of the tip of a ballpoint pen. So I have to find a way to change my band gap and tune it to a different color of light without ripping it apart in an atomic level. And to do that, we have to think about what my LED is actually made of. My deep yellow LEDs were made of this compound, gallium phosphorus arsenate. Now, if you look at the periodic table, we can see that all of these elements occur in a very similar area. Now, conductors or metals usually sit on the left side, where non-metals sit on the right, but there's a small stair step where the metalloids exist. And all semiconductor materials are made of these semi-metals, like indium, gallium, arsenic, and phosphorus. Now, my semiconductor is called a 3,5 because it's made from elements in groups 3 and 5. And these tiny little numbers just represent the doping process, how much of each of these elements are inside the compound. Now, all I have to do is manage to stretch the band gap of this compound to make it change color. Except the problem is that this is what's called an ionic compound, meaning it's made of a lattice, a rigid structure of nuclei and electrons that are very hard to break. These ionic compounds have high melting points. Just think of table salt. Have you ever tried to melt table salt? It's nearly impossible. So how am I going to change the structure of the lattice, to change the band gap, to change the color of my lights? Well, to that we gotta think about temperature. I'm gonna save you a lot of guesswork and tell you right away that the answer to this has to do with the cold. Watch what happens in this video when I put one of my deep yellow LEDs into liquid nitrogen, which is about negative 320 degrees Fahrenheit, give or take. Did you see it? The LED changed color when it got put in the cold liquid nitrogen. Now, why is that? Well, let's think about what happens to structures as they cool. As the temperature cools in a structure, the vibrations holding the structure together slow down, which means the structure condenses. Now, in this very simplified graph, we're gonna show you that the ionic lattice of my semiconductor closes in the cold. This pushes the electrons closer together, which causes them to overlap in their orbitals more, which creates deconstructive interference that pushes themselves apart, increasing the band gap. And now when this band gap increases, the energy of the light needed to cross the band gap increases as well, which then turns my deep yellow semiconductor into a nice spring green. Still cut. Did you also see what happened? As I put the light in the cold, its intensity increased. Now, why would that happen? Well, the simple explanation is LEDs are already very efficient, and they give off most of their energy as light, but there's still some heat generated, and the cold of the liquid nitrogen caused all of the electrons moving across the band gap to be turned into light rather than heat, which caused the intensity to increase because of the more photons per second. Hey, what are you doing? We're almost done. Get over here. And on me. Jesus. You're not getting that $5 meal coupon. Anyway, so in conclusion, is this a good way to change the color of my lights? Is it effective? Well, I'd have to submerge my lights in liquid nitrogen every single day just to maintain their color, so obviously not. I probably have to live with my poor monetary decisions. But you know what? We did learn something, didn't we? The quantum mechanics of LEDs, these lights that cover our cities, on the backs of our phones that are everywhere, are very, very incredible. That we can make something that fits in the tip of a ballpoint pen that can produce light on the quantum scale is just incredible. So, I'm probably going to buy some new lights, but you know what? I'll just keep the yellow ones. And as always, thanks for watching.